let's look at this question. So we have a cantilever beam fixed at wall support. So if we see this support is A support, and then the free end is restrained by this roller support. If we say this support is B. Okay, so in this question, it also provides the free body diagram with reaction force and applied moment M showing here. So look at these free body diagrams and the reaction force. We find at support A is fixed support. We suppose we'll find 3 reaction force here. So one reaction force in shown here is a reaction force in vertical direction, RL. So the second reaction force is a reaction moment, MW. And also there is a reaction force in horizontal direction, that is, we say AX. Okay, so in this question they didn't put AX on this reaction force. Here is the reason. So if we write down the equation of equilibrium in x direction, so Fx equals 0, so all in horizontal direction, we find there's only one force, that is AX equals 0. So we find AX equals 0, so in this question AX is not put on these free body diagrams. We can just delete this force as well because it's 0. So also we can write down 2 other equations of equilibrium. So if we write down equation of equilibrium in y direction, we will have RL equal to RR. Okay, this is the second equation of equilibrium. And the third equation of equilibrium, we can write down the moment equation of equilibrium. Suppose, so if we write down the moment equation of equilibrium in support A, so in the fixed support, we will have the, if we see the clockwise direction is counterclockwise, it's positive. So at support A, we have MW is positive, and we have applied moment M is positive as well, and also the reaction force RR have a bending moment at support A, but it's go clockwise direction, so it's negative RR times the lever arm is L equal to 0. So this is three equations of equilibrium we can write down. We already know AX equals 0, so we don't consider it here. And now we have 2 other equations. So in these two equations, we have 3 unknown forces, RL, RR, and MW. So we cannot solve it just by 2 equations for 3 unknown forces. So we need to find additional equation to help us to solve 3 reaction forces. Okay, so here is the solution. So we can use the double integration method to find out an extra equation to find this to solve the reaction force. So first of all, if we cut this beam arbitrarily at some section A to A, and we build up the coordinate systems y, x, so the cutting at some distance is x. Okay, so after we cutting this beam, so we can draw the beam segments over here. So this beam segment cut at A to A. Okay, so on this beam segment we have a reaction force RL, have a reaction moment MW, and we have a bending moment, if we say, is mx. Okay, so because this is internal bending moment is a function of x, and the distance, we know that the length of this beam segment is x, and we can draw the shear force over here, but we don't consider it here because we don't use it. So based on this beam segment, we can, so if we write down the equation of equilibrium of bending moment at section A to A equal to 0. If we see in a counterclockwise direction is positive, so at section A to A, or this section A to A, we have a bending moment MW is positive, and the RL have a bending moment, but it's go clockwise direction, so it's negative. And on this section, we have internal bending moment is mx is go counterclockwise direction is positive. So this equation we will derive the internal bending moment mx is equal to negative mw plus rlx. So once we know this internal bending moment, so we know for the elastic beam we have derived this equation d square y over dx square equal to mx internal bending moment over ei. Okay, so if we put ei on the left hand side of this equation, we will have ei dy square dx square equal to mx, and mx we have derived mx is shown here, so it's equal to negative mw plus rlx. So we needed to do two integrations. So first integration we do it on both sides of this equation. We will have ei dy over dx equal to negative mw x plus 1 over 2 rlx square. We have a constant c1, and we do second integration. We will have ei y equal to 1 over 2 mw x square plus 1 over 6 rl x cubed plus c1 x plus c2. So based on our knowledge on double integration method, we need to evaluate the c1 and c2. This is two unknown constants. How to evaluate? We just need to use the boundary conditions. So the boundary condition we can use is showing here. So at this fixed support, support A is fixed. So we will have, if we have zero deflection of this fixed support, x equals 0, y equals 0, and we have zero rotation, x equals 0, dy over dx equals 0. So by using these two boundary conditions, we can solve the unknown constant. So now we apply these two boundary conditions. So x equals 0, y equals 0, then we can solve. So if we plug in x equals 0 into this equation, y equals 0, we will find c2 equals 0. If we apply x equals 0, dy over dx equals 0, we apply this boundary condition into this equation. We will have c1 equals 0. Okay, so in the end we get the equation is that. So we have so we can just delete c1, c1x, c1, c2. So then we got two equations. One equation is the equation of a slope. The other equation is the equation of deflection. So how we use this equation to find out actual equation to solve the unknown reaction force? Here is the solution. So from this beam, we find we have using the boundary condition on support A. And also look at support B, we find support B also have low deflection. That means x equal to L, the deflection is also equal to 0. So using this information, we can find the actual equation. So we apply this boundary condition, x equal to L, y equal to 0, into this equation. So if we apply into this equation, we got x equal to L, y equal to 0. So if we apply, so y equal to 0, so on left hand side of this equation is 0 equal to x equal to L 1 over 2 mw x square L square plus 1 over 6 RL L cubed. So this equation is equation for mw and RL. Let's simplify this equation. We will find RL times L is equal to 3 mw. Okay, so we got one extra equation. So using this equation and this equation, we can solve mw. So we just solve here. So if we just plug in here, so from this equation we know mw plus m minus r L equal to 0, and RL, so showing here RL equal to RR, so we can just change here, so it's equal to RLL equal to 0, and from here we know RLL equal to 3 times MW. Okay, we put it here, so it's MW plus M minus 3 MW equal to 0. So we got MW equal to 1 over 2 M. Okay, so we got this result. So this is a bending moment at the wall support MW. Once we got MW, we can solve RL. So RL is equal to, shown here, so 3 MW over L. So it's 3 MW over L is equal to 3M over 2L. So this is a reaction force RL, and RR equal to RL. So this is the reaction force showing here. Okay, so in this question they said the M is equal to 25 kilonewton meters, L is equal to 5.8 meters. So if we apply these two information into these two questions, we can derive the vertical reaction force at wall RL, and we can derive the moment reaction force at wall MW. So once we derive it, so we plug in, so RL equal to 3M over 2L. So M is 25 kilonewton meters, so 3 times 25 over 2L, 2 is 5.8. So this we got some results about kilonewton. Okay, once we're using calculator, we can solve that is 6.47 kilonewton. So this is positive, it's go up is positive. So this is RL. MW is equal to 1 over 2M. 1 over 2 times 25 is 12.5 kilonewton per meter times meter. Okay, so this is the solution, RL MW. So this is the step-by-step solution for this question. Thank you.